The HackRF Spectrum Analyzer with Jared from sharebrained.com. This segment of Hak5 is brought to you by domain.com.
Mad science territory here.
I love mad science. Oh, you weren't joking.
Yes, this is the guy.
That's it? Wow. Yeah, it does. It is kind of like the battleship of software-defined radio, because it's just like kerchunk, kerchunk, kerchunk. Like, it just needs more accoutrements plugged in, like the antennas and everything.
Mm-hmm. Well, I got antennas. Yeah, this is a great way to build stuff, though, because...
Well, it's modular.
Yeah, we can isolate each individual portion, bring it up, defer some design decisions until later. So, turns out we had like a different front-end design here. Didn't work out very well.
Oh, is this guy over here?
Yeah.
What was wrong with this?
It's so long ago I kind of don't remember.
It's totally cool.
But yeah, there were like at least 2 iterations on this guy. Osman's original intent was to create something that required very little in the way of hardware skills and was inexpensive. So that meant having a single assembly that was already completely integrated, didn't have any expensive connectors, didn't have multiple assemblies that had to be manufactured separately.
Right, it makes a lot of sense. The idea here was you'd be able to, like, oh, you want a different band? Swap out this piece or that piece, right?
Well, yeah, that's certainly a possibility with this design. However, his design intent was just to be able to cover all bands.
Yeah.
That's ultimately what he wanted to work toward, is having a single board that would just do everything. Maybe not the best at everything, but good enough that people can, for security research, do whatever it is they want.
So this is where you do it?
That's where I do it. Yeah, most of my time is spent facing the wall.
Yep. Gotta love the stand-up desks.
Yeah. Yeah, this is a IKEA Frederick desk that I think was...
Right.
No, it's pretty much straight up, but I don't think they intended for it to be set this high. I think it was much more designed originally for sitting. Mm-hmm. So, I'd love to have more space.
Yeah.
Because I've got, 2 computers here, 2 displays. My oscilloscope, I wind up having to, I've got a board up here I'm working on. And so I'm down here with the probe, looking at the oscilloscope and doing this, and trying not to short stuff together. And then the keyboard's in the way. Yeah, it's not ideal for working on hardware, but this is a desk made by a local company called Anthro that has served me well. The problem is I just can't turn it into a standing arrangement. So it's pretty much just my soldering workstation.
I love the standing arrangement. It's what's up. Well, you want to show me the Spectrum Analyzer?
Yeah, absolutely. It's a good place to drop this.
Yeah, anyway, if you want to set it on the table, or, there's great light in here with the sun coming in. It's like natural. So what are you doing on the laptop?
So the interesting thing about the way the Jawbreaker works is the ARM controller on it doesn't have any internal flash of its own. There is a SPI flash that you can use to bootload code off of, but for whatever reason, the code that I hacked up to run the display here doesn't seem to run right if loaded from flash, but works just fine if it runs from RAM. So I'm using a little debugger that...
Is that this guy? This board?
No, that's a different story. It turns out the debugger's in my bag, because I was going to bring it along to do some JTAG, or actually serial wire debugging on the Daisho board. And obviously we didn't get around to that. So now I got to go and grab that out of my bag. So this is an ARM serial wire debugger. It's a Black Magic Probe guy in, I think, New Zealand. Designs and manufactures it, and it's, I think, the best way to roll as far as ARM debugging goes.
Oh, okay. So that's so much more advanced than just a serial TTL. That's giving you what out?
So it provides a way to load code into RAM, to load code into Flash, and then to control execution of a program. So, it's a full GDB environment. It acts like a serial console. You connect GDB to this thing.
Oh, nice.
And then
so
you just do
you
single
don't even have to
steps.
think about, like, it's the intermediary.
Yeah. Yeah, so it's like, you just plug it in and you open it up as a serial console in GDB.
GDB is what debugger?
The GNU debugger.
Ah, the GNU debugger.
Yeah, so GDB just issues commands that this thing understands. You can do single steps, you can do flashing of code, you can look at registers. You can
It's
do
the
all sorts
ultimate debricker.
Yeah, exactly. And it's just so simple because it's just an ARM microcontroller itself. And it's really small. You don't need any additional software.
That's funny. So to speak to your ARM microcontroller here, you use a smaller ARM microcontroller here.
Yeah.
Yeah.
Yep.
You're like, hey, you know what speaks great to ARM? ARM.
Yep. Okay, so just loaded code up in GDB.
So what does that look like? Oh, I see.
So yeah, this is GDB with a --TUI option, which is the text-based UI.
So you're actually telnet or whatever, you're over serial in this console here, over to that board in there, and you're looking in like an editor at some the vector.c file here?
Yeah, so this is the source code loaded up in GDB. GDB is communicating via serial to the Blackmagic probe.
Here we go. Yeah, load section, ARM, And so this is kind of like being into a bootloader, except it's not a bootloader. It's a...
With a serial wire debugger, you're talking a variant of JTAG, and you're essentially just brain tapped straight into the CPU. So you've got the ability to manipulate the core elements of the processor, ability to read and write registers, and set it up to do whatever you want. So it's really nice. It's great for debugging. It's this kind of stuff that I really miss when I'm dealing with like an Arduino, because it just doesn't have full-blown debug support. And so that's why I like working with ARM.
And so you're just using that because this is kind of like a proof of concept demonstration thing. This isn't like, a flip the switch in it. It's not supposed to be like this is just a demonstration of one of the things it can do. And so rather than write it as a program where it's like you power it on and it does this, you just load it this way.
Yeah. All this. So originally I threw all this stuff together just to show at the Bay Area Maker Faire. I thought I was going down with the Dorkbot booth, Dorkbot PDX booth, and I wanted to get a cool hack together. So I had this vacuum fluorescent display that I'd bought from the Noritake online store. I didn't at the time know what I was going to do with it, but like a week and a half ago, realized, I should hook this up to the HackRF, do some basic spectrum analysis on whatever radio frequency I'm tuned to, and then just display it on the VFD. I think it looked really cool.
So what radio frequency are you tuned to?
Well, we'll get to that. So I, before I went down to Maker Faire, I had this laser cut wheel all set up and ready to go. My vision was I was going to have an optical encoder, kind of like in the old mechanical mice, where you could just spin the wheel around and change the tuning frequency. It didn't come together in time.
Like a radio dial, literally.
Yeah, giant radio dial.
Nice.
And actually, once I get it fired up, you'll see it really feels cool to just sort of, just jog back and forth through the spectrum and watch stuff move back and forth.
It's like a big iPod wheel.
Yeah. Okay, so I'm going to hit continue on GDB, and the code should just start running. There we are. Yeah, so right now it's tuned kind of in the middle of one of the cellular bands, 840 megahertz. And there's not a whole lot going on. Oh, hey, I don't have my antenna extended. Maybe I'll do that. Probably won't make too much of a difference, but yeah.
And
so,
is that antenna right there attuned to 839 megahertz?
No, it came with an Icom PCR 1000. It's a radio designed for hams, but it was designed to be controlled from a computer, and it was designed to tune to 100 kilohertz all the way up to 1.3 gigahertz. So it's kind of a general purpose antenna. Yeah. It doesn't perform all that well when you get up above about 2. So if we get into the Wi-Fi region, it's
show me. So how do you tune this thing?
You just turn the wheel back and forth.
Oh my god!
Yeah.
Look at that.
So I wrote down a few days ago some of the different frequencies, like FM radio. Yeah, I spent some time on the FCC website.
Of course, those guys
started
have
looking
all
up stuff. So there's all the FM stations around here, and then there's all the TV stations. There's these channel numbers that I had to map into frequency ranges. But if we slide around a little bit...
So if we get to 566 to 572, we'll be tuned to KPXG.
Yeah.
Which is like, what, a local CNN affiliate or something?
I think KPXG is actually a religious station.
Oh, right.
But that looks like a TV
wow.
station right there. It should be about 6. So each of these ticks is a 1 megahertz interval.
Okay.
So, I'm tuned to about 675 here. That'd be 674, 673, et cetera, et cetera. Along the left side here, I'm taking the raw sample value minimums and maximums for the 2 sampled channels and just rendering them out. So I can see whether my gain is too low or my gain is too high. If these things were just solid bars from top to bottom, I would know the gain was too high and I need to turn down the input gain on the RF amplifier. So yeah, it may not be a station. Let me tune. Oh yeah, there we go. Yeah, that's about 5.5, 6 megahertz. Yeah, which is about the bandwidth of a TV station. So that looks like 656 to 662, which is KNMT channel 45. Tune down a little bit more. Looks like
And
we got
so now
another
you can
station
just,
here.
center it up. You could, with HackRF, pick that band, pop it into like GRC or, GNU radio and just tune it to the right modulation.
Totally.
Well,
Yeah.
I mean, okay, back in the analog days before TV became digital, it was a little easier, but now what do you use, ATSC?
Yeah, this is ATSC. So one of the first things that was ever done with GNU radio was ATSC decoding.
Oh.
So I don't know if they've kept the decoders in GNU radio up to date, but I imagine they have. So something that I would like to get around to is taking one of these 6 megahertz channels, digitizing it onto the host, and then just running it through GNU radio to see if I get the TV.
That would be awesome here for your display too, because you would have the radio dial as you do right here, where you're, choosing a frequency, and then like you could have an LCD screen here. And the interesting thing about ATSC is it's kind of an all or nothing affair.
Yeah, like most things digital, it seems.
Yeah, but I wonder if you just tweak it off just a slight bit, if you could get some cool, I don't know, effects, some weird glitchy stuff.
No, that was definitely true with NTSC because the signal was just intrinsically more sort of favorable to those kinds of misbehaviors. But with ATSC, you get, if you tune too far off frequency, it's just not going to decode. You're going to get lots of macro blocking like you would, if your satellite reception goes poor. So yeah, I don't know that you would get much interesting. It would just sort of freeze up.
Well, okay. But you could put a speaker on this thing and do it for FM, frequency,
Yeah, I would
or AM and do like amplitude modulation and scroll through and get like the ball game.
Yeah, I'd love to build this out further and provide some sort of audio output. So when people
Well, it's so
around,
visual right now.
Yeah.
And so tactile with that giant wheel. I love this too. How is this working? So you've got 2 photo
yeah.
sensors on here?
Yeah, so this is based on your standard optical quadrature encoder technique. If you took a computer mouse from 15 years ago, before they all started being built around optical image sensors, you would find a wheel very much like this with a whole bunch of little cutouts in them, and then 2 optical encoders that are offset to some degree. And if you were to graph out, I don't have my dry erase marker on me right now, but if you were to graph out the sort of make break or the black and white areas as I rotate this, you would see a particular pattern that looks, as you turn the wheel, I still haven't figured out the really good way to explain quadrature encoding.
No, I totally get you, because you can, with the 2, you can tell what direction it went.
Yeah, exactly. So yeah, it's like, if you see the first signal go high and then the second signal go high, that means you're going one direction. But if you see the second signal go high and then the first signal go high, you're going the other direction.
You see the same thing actually when the Department of Transportation puts those lines here, like these cables that go across the road. There's always like 2 cables, and they do it when they're doing traffic analysis. And so like if a car hits this cable, then hits that cable, it was going this direction, but if it hit this cable, then that cable, it's going that direction.
Exactly. Yeah, it's like you see a pulse on A and then a pulse on B, the car's going north, and if it goes B and then A, yeah, it's the same basic concept. There's, and in fact, there's also an analogy for how the radio works here.
Okay.
The radio signal is being digitized in what's called a quadrature fashion. So you've got these 2 channels, I and Q, which, because of the way they're processed, yields something similar. You have a bunch of samples that you get out of the radio digitizer, and depending upon how the 2 signals you've digitized relate, it represents either a positive frequency or a negative frequency. And that's why when you look at this display here, I'm showing frequencies above and below the frequency that I'm tuned to. It's a little much to get into,
right.
in a radio sense, because it's very hard to visualize radio as opposed to, like this optical wheel or the sensors in the road you were talking about. But yeah, it's all sort of based on the same idea that, if one signal comes before another signal, then that means it's going this way, and vice versa, it means it's going the other way. So let's tune down.
Can you take it to 2.4?
Oh yeah. This will take a little while, but fortunately this thing will tolerate me spinning it pretty fast.
Wow, look at all of that stuff. I'm surprised how much dead area there is, I don't know if it's because of the antenna or there's just that much unused frequency.
Well, a lot of the stuff's
2 gigahertz, 2.1,
2.2, 2.3,
2.45 is the center of Wi-Fi.
Yeah, so we're right at the bottom edge. There's
So
nothing
this
going
is
on.
like channel 1.
Yeah, I saw a little blip of something right above. Yeah, it would be like channel 1 would be plus and minus what, 10 megahertz?
Well, here, I'll turn Wi-Fi on my phone. And I'll do
I
a
could also
scan.
download something on my laptop here. Let's see. I know. How about a YouTube video? Whatever's on the top today. Okay. I'm trying to remember what channel my Wi-Fi is here.
11, 6, 1.
Yeah, I think it may be configured to jump around based on what's best.
2.45 is the center, but you're only looking at 1 megahertz on each of these ticks, right?
Yeah. So let's...
Oh,
there we go.
yeah. So all of that jumping is actually... You're looking at the spread spectrum right there.
Yeah. So yeah, that's the spread of the signal across.
So you're literally seeing ones and zeros.
Pretty much. I mean, it's...
What's the refresh rate on this?
Well, that's the funny thing. So because of CPU limitations, I'm digitizing only very brief chunks of data. So I'm getting maybe 1/20th of the total time that, over a second, I'm only digitizing maybe 50 milliseconds worth of actual data. And the rest of the time I'm spending processing it, running it through a fast Fourier transform and doing all of the manipulation for the display. So really, a whole lot of the traffic that's taking place, I'm just completely missing.
Right.
So it's definitely much better if there's really sustained traffic or a continuous transmission. You can see that just locked on there. But for Wi-Fi, other stuff that's really bursty, it'll show up periodically, but a lot of the packets will get missed. So the proper way to do this, if it wasn't a complete hack, would be to just continuously sample and then probably like average or accumulate the spectrum over time. Just add the samples together in blocks, and do some sort of averaging or peaking or something like that. But it was a hack for Maker Faire, and frankly, Maker Faire there was so much Wi-Fi that this thing was pretty busy anyway. It was a very intense experience from an RF standpoint. Just tons and tons of Wi-Fi, tons and tons of Bluetooth.
That's fantastic.
Yeah.
Oh yeah, we should go down to 900.
Yeah.
915.
See if we can find much. We can also go down to FM. I mean, it's not all that sexy to look at the FM band, but at Maker Faire, people were kind of blown away when I would say, "So you're from the Bay Area, right? You know all the FM radio stations," and then I would go through and tick them off each peak, and I would say, "So 99.5, 101.1, 103 and they would say, "Yeah, those are all radio stations." And I could just tell by looking at the display.
Nice. This is like Wheel of Fortune too.
Yeah, dialing for RF. So these should be pager signals. Yeah, just below 930. Both of these little bits here. Another thing I wanted to do with this project, didn't have enough time, is to have some sort of a gain control. You can see over here on the minimum and maximum display, the signal's really weak. But still, we've got signals that are right in the frequency range that pager data should be located in. So, some doctor somewhere or some IT professional's getting a page telling them that Mr. Smith's having a heart attack right now.
Wonderful.
Yeah. Let's see, what else have we got around here?
Garage door openers.
Possible.
And all sorts of other stuff.
It looks like someone might still be rocking an analog 900 megahertz phone at home, a cordless phone.
Nice. Let's tune to, what did they use? FSK or?
I think it's probably just FM modulation.
Yeah.
Or FM. Yeah, so I'll bet you that might be someone using a cordless phone. And then we've got some cellular data here. We're down, in the 800 range. Various data and voice conversations.
I love how this just kind of like visualizes it in such a tactile manner where, yes, you could fire up a new radio and do the same thing with even a very cheap DVB-T dongle, but it doesn't have the scroll wheel and the giant display.
Yeah, well, and also having the bandwidth that HackRF is able to pull in all at once is a big deal.
Even if you're squishing everything through an intermediary like 2.4 gigahertz, you're still getting a decent enough sample rate that you can do fun stuff with, like, say, ADSB or all sorts of other fun transponders. So you were just talking about the marine one.
Yeah,
with all the big ships.
AIS. Yep.
AIS. So I could find out what all those oil tankers are carrying and where they've been and where they're going.
Exactly, yeah.
They're probably carrying oil, but,
Yeah, and here on the Columbia, half of the boats that you see are probably barges taking garbage and recycling upriver. Not too exciting, but yeah, just the fact that these boats are sailing around and you can just pull that data right off of the boats as they're going upriver.
Yeah.
So right now we're tuned to the FM band, and we've got 100.3, 101.1, 101.9, 103.3, 104.1, 105.1, 105.9, 106.7.
So each of these peaks is another radio station, so that really illustrates how small the bandwidth for FM is.
Yeah. And something cool to do. So this display, obviously, it's kind of grainy. It's a 384 by 32 pixel display, which for a vacuum fluorescent display is actually really amazing. But if you were to graph this out on a computer, do some sort of a waterfall display, you can see how the digital modulations for HD radio have been added to the existing FM transmissions. You'll watch and you'll see this sort of jiggly pattern right down the middle. That's the original FM, the analog signal. And then what they did with HD radio is they added these two digital modulation sidebands. And so you see these weird little strips of noise along the analog signal range. And so you can just look at the graph and well, that radio station's got HD. This radio station's got HD. That one doesn't.
What's the modulation for FM radio in HD?
It's some proprietary thing.
It's kind of like the ATSC equivalent for audio?
Yeah, well, the modulation's not proprietary. I mean, there's only so many modulations. It might be OFDM, but I don't frankly recall.
Yeah.
But it's constructed such that the modulation, the data winds up getting pushed outside of the analog range, so that old analog FM receivers
don't even notice it. They don't even create a crackle on the stereo.
Right.
That's
and
cool.
so they're just sort of hanging along on the sides, and the digital HD receivers are capable of pulling that stuff in and demodulating it.
And so to an FM receiver, it would just sound like, as you're turning the dial, it would just sound like a little bit of white noise in between them.
Yeah, although
a little static, which you're used to hearing static anyway.
Well, on FM anymore, most radios seem to blank, so you don't really get much in the way of just even background noise. If the PLL can't lock into the FM, it just doesn't actually play back anything out of the audio output.
Mm-hmm. And so you were able to do how far with the HackRF? So we're down in the FM zones, but if we really jog this down, we're at 30 megahertz, 20, 19.
Well, the tuning right now
it
looks like there's some sort of bug.
10.
Well, you'll also notice that as I scroll up in 10, really the peaks don't move anywhere.
Oh, I see.
So I think there's a bug still in the firmware as far as the tuning goes. Once I hit 30, suddenly the stuff starts moving.
Mm-hmm.
But it also moves the wrong direction. So this is still beta. Mike Osman is shipping out tons and tons of beta units as we speak. And the intent is to get it into as many hands as possible so that we can find bugs like this and address them in the firmware, or if necessary in the hardware too, and make the radio tons better. So we're really looking forward to this phase of the project because we're going to get a lot of feedback. We're going to find all the weird bugs and stuff and get them resolved, and this thing will suddenly be so much better as a result.
Yeah.
Yay, open source.
I love that. I mean, and also the way that you guys have spent so much time, as we just saw with the previous version before the Jawbreaker, so much time on the hardware that I can only see this as like a long-term like LTS or whatever. So hey, where can people find a HackRF if they aren't part of the beta? Where can they sign up to get one maybe?
Well, so HackRF is a product of Great Scott Gadgets. DARPA supported the project development, but ultimately...
We like DARPA, they created the internet.
They did. So Great Scott Gadgets is the website that you would go to, greatscottgadgets.com/HackRF. And then there's tons of links from there, including a link to the GitHub repository where you'll find the schematics, the circuit board layout, the firmware for the ARM microcontroller, the host code that you would compile onto your PC. Everything is there. I haven't yet posted the code for this, but it's so awful that I'm not sure I ever would.
Well, it looks awesome. So thanks so much, Jared, for sharing it with me.
Thank you.
Budding entrepreneurs, startups, innovators, they're all turning their ideas into realities using the strength of a .NET domain. See, .NETs are globally known. It's one of the most popular domain name extensions, and .NET domains inject your business with instant credibilities. Entrepreneurs and startups are immediately discovering the advantages of building their web presence around a .NET domain. So if you already have a .com, well then purchase the corresponding .NET to protect your brand, and if the .com you want is already taken, well then register a .NET. It's a perfect alternative to registering like a 50-character .com. That's not gonna fly. Now you can find yourself a .NET domain over at domain.com. I love these guys. They've got affordable, domain names and hosting. .NETs are only $8.99 a year. They're reliable. They're easy to use. They're a lot of fun to do business with. They're active on Twitter at domain.com. It's really just a great place to do business, and they are huge fans of Hak5, so they want to hook you up with an awesome 15% off their already affordable domain names and hosting. All you have to do is use the coupon code HAK5 at domain.com's checkout. That's 15% off and big savings, so don't forget to use coupon code HAK5. When you think domain names, think domain.com.
Last week's trivia question was, which wireless standard can operate at speeds of 100 plus megabits per second and uses the 2.4 gigahertz to 5 gigahertz range? And the answer I was looking for is 802.11n. This week's trivia question is, what man-in-the-middle attack exploits address resolution protocol? And you can answer that over at hak5.org/trivia for your chance to win some awesome Hak5 goodies.